So which one of the following is not expected to be an intermediate of the following reaction? So first, step one is obviously finding the leaving group. Which leaving group departs? Obviously it's IH. So iodide leaves from 1 iodide 2 methyl cyclohexane, this giving a secondary carbocation at the carbon that originally held I. So option D is of course an intermediate. Then the rearrangement, step 2. So the carbocation in option D is secondary and adjacent to the carbon bearing a methyl group. Thus basically. So the proton heads over there. A hydride shift occurs from methyl substituted carbon to a carbocation center. This moves the positive charge onto the methyl bearing carbon, producing a tertiary carbocation. So option B is also an intermediate. Then step 3, the nucleophile attack. The water attacks the tertiary carbocation, which gives a protonated alcohol, which is this. So the protonated alcohol is obviously in this. So now what about A? A shows a carbocation on a methyl bearing in carbon without rearrangement, accounting for how it got there. So this is not an intermediate. So this is the answer. A JE means trick is whenever you see a leaving group leave, then a carbocation is formed. The adjacent carbon can form a more stable carbocation. So you have to check the hydride shift before methyl shift. Here in this case, it goes from being secondary to being tertiary. So this is favored rearrangement leading to option B instead of leading to option A. Now we have an SN2 plus Fischer reproduction. Here N sodium iodide with acetone is reacting. So this is Finkelstein reaction. So in Finkelstein reaction, the I replaces the other halogens. Here in this case, it's Br. So, and this is a SN2. Remember that SN2 has Walden inversion, meaning it does a 180-degree flip. So in this case, the product will be something like this. The H comes over here. Br is replaced with I, so I comes over here. H stays here, CH3 stays here. So now which one of the following matches that answer? B does. So the answer is B. Now the rate of SN2 is negligible. We know that SN2 requires the backside attack, and if the carbon is bearing Br2 is attached to an sp2, to a carbon of a double bond, like LEF or vinyl, like restrictions or geometry blocks the backside attack, it becomes very difficult. So let's say cyclohexane bromide. SN2 is slow, but the CBr, the carbon here and Br here are on normal saturated carbon. Now we have LEX bromide, the Br bearing carbon is adjacent. is adjacent to the double bond, adjacent over here. Then the halides generally undergo SN2 quite readily because of the transition state is resonance stabilized. So SN2 is possible. Now this is the bridgehead halide or Nor-Borne type system. The carbon bearing bear is at a bridgehead. For SN2, the nucleophile must attack from backside, but the bridge physically blocks it. So this is not possible. Because the backside attack is essentially impossible, the rate of SN2 is approximately equal to 0. Therefore, not possible. Now for the Eliac halide once again, SN2 possible. So the answer is C. Now, what is the major product obtained in the following reaction? We have O-bromobenzyl bromide reacting with NH3 and ethyl alcohol. ET means ethyl, by the way. So the two possible substitutions are replace benzylic CH2Br or replace aryl bromide. So which one reacts? The aroma, the aromatic ring CH2Br is highly reactive towards SN2 because the benzyl transition state is resonance stabilized. But aryl bromide does not undergo ordinary SN1 or SN2 because of the sp2. So replacing aryl bromide would require nucleophilic aromatic substitution conditions which are absent here. Therefore, the only reaction is this occurs, which means the ring remains untouched. So the product is A. Now, for this type of questions, remember that bridgehead means SN2 is impossible. Yeah. And for this, remember that benzylic halide plus NH3 is amine formation, and aryl halides do not undergo ordinary SN1 or SN2 readily or at all. Okay. Now, this is another Finkelstein reaction. DMF is an polar aprotic solvent. So I is a strong nucleophile that favors SN2. Of course, it's Finkelstein, so it's SN2. So now, which Cl is substituted first? There are only two primary Cls. Let's say this is site A and this is site B. At site A, the carbon bearing Cl is adjacent to a quaternary carbon, and the backside attack is heavily hindered by a bulky CH3 groups, two of them, which means the SN2 is extremely slow. Now for side B, normal primary flora SN2 occurs readily, or in simple terms, which one of these two are far away from the bulky reagents? Side B is. So side B is replaced by group I. Therefore, I attacks the terminal primary chloride at side B. This corresponds to option B. Now, which one of the oh wait, no, let me give you a shortcut here first. SN2 is usually slow despite being primary because the adjacent carbon is extremely bulky. So whenever you see XnCH2, Cr3 or a neopentane halide, You have to think in this manner. Now, question number 6. SN2 stands for bimolecular. So if you watched my other video, you would have noted that bimolecular meant there are two things that are in the rate reaction. Here in this case, there is only option B. So option B is the answer because it only has two other things. Electrophile basically means anything with an extra proton. Nucleophile means anything with an extra electron. Now for question 7. The starting compound Br and Fr are on opposite sides of a carbon cyclopentane. The reagent is NaI and acetone. Again, Finkelstein reaction. The key factor here is Ri is greater than Rbr, which is much greater than Rcl, which is much greater than Rf. Fluoride is an extremely poor leaving group, so only I gets replaced by Br. Once again, stereochemistry. SN2 causes inversion, meaning the answer will be something like this. So the answer is option A. Oh, wait, no, I did it reverse. My bad. The I goes over here and H comes over here. So the answer is option A. My bad, guys. Anyways, now for question number 8. Which one of the following alkyls undergo rearrangement in SN1 reaction? Option A. The loss of I gives CH3 dash C. I'm just gonna write in bracket form. This is a secondary carbocation adjacent to a quaternary carbon. Quaternary basically means this. So a 1,2 methyl shift occurs, meaning secondary goes to being tertiary. So rearrangement occurs. Now for B, the loss of Cl gives a tertiary carbocation directly, so there is no driving force for rearrangement. This does not happen. So now for an allylic iodine, loss of I gives an allylic carbocation. The positive charge is stabilized by resonance and not by rearrangement. So there is no rearrangement over here. Option D, say B and C are not possible. So not possible. Now for the okay. Now for the decrease in order of SN1 reactivity among the following. One, this is a primary. SN1 very difficult. Now, 2 is an allylic chloride. Carbocation is formed and is resonance stabilized. So, very favorable. Now, for 3, it's a secondary chloride and it forms a normal secondary carbocation. Since allylic is greater than secondary and primary, therefore, the answer is option B. Now, which one of the following compounds undergo nucleophilic substitution reaction with NaCN at the fastest rate? NaCN is a strong nucleophile, so the reaction mainly undergoes in SN2. So, first A, primary bromide is primary bromide, but the branching is far away. There is a lot of branching. So, it's a good substrate, SN2 substrate. Now for B, it's a secondary, so it's lower. Now for C, the primary bromide is directly adjacent to a highly branched neopentane-like hindrance. So SN2 is greatly slowed. Now for D, a tertiary bromide. If it's tertiary, SN2 is basically impossible. So the answer is option A. Now rank the following in order of decreasing of solvents with an aqueous solution ethanol in fastest to slowest order. Now, if the word solvent appears, that means it's generally SN1 favored. So we have to complete the carbocation stability. One is a vinylic bromide. Br is directly attached to an sp2 carbon. So the loss of Br would give us an vinylic carbocation, which is uh, extremely unstable. So SN1 is very slow. Now for two, one bromo, one methyl cyclohexane. The loss of Br gives tertiary carbocation, which means SN1 is the fastest because it's highly stable. Now for three, this is a secondary bromide. The loss of Br would give a secondary carbocation, which is an intermediate. Therefore, it goes in the order 2 greater than 3 greater than 1. That means option C. Now for question 12. Hmm, the substrate with NaCN and ethanol, the CN minus will attack the benzylic chloride by SN2 and the aryl beer does not react under these conditions. So PBr C6H4 minus. This is option A. 4 bromo benzyl cyanide. So now, which one of the following reactants will not be favorable in a nucleophilic substitution reaction? Now, this is a straightforward answer. One is a bridgehead bromide. That means, and this is the Norbonyl type, not in syllabus. Don't worry about the names. So, SN2 generally impossible because the backside attack is blocked. SN1 would require a bridgehead carbocation that's highly unstable. That is known as Bredek type restriction, also not in syllabus. Don't worry about the names. So the substitution is generally not favored. Now, PH bromobenzene. Aryl carbon is sp2. So SN1 phenyl cation is impossible. SN2 backside attack on sp2 carbon is also impossible. Now for C, neopentyl bromide. SN2 is very slow due to steric endurance. So CH3 and Br are generally not favorable here. And SN1 would require a primary carbocation, also highly unfavorable. So does not favor substitution. All of the above. Now for question 14. This is the famous SN1 versus SN2 trap question. The substrate give is 9 bromo dash 9 10 dihydroanthracene type system. So the carbon bearing beer is extremely special. First question you have to ask, is SN2 possible? For SN2, the OH has to attack from backside of the CR-Br bond. This is a fused ring system. So the carbon is buried inside a rigid polycyclic framework. The backside attack is also blocked by the bridge ring or framework. So the backside attack is essentially impossible. So SN2 not possible. So what about SN1? If Br leaves, you get a carbocation at the bridgehead like carbon. Now, if that happens, the positive charge becomes delocalized over the aromatic framework. The resulting carbocation is highly resonized. The entries type benzylic stabilization. You can also draw several resonance from forms where the charge spreads into the fused aromatic rings. Therefore, R dash Br gives R plus 1 is favorable. Then R plus OH minus gives R dash OH, giving the product. So now you might be asking why SN1 is favorable here? Because the intermediate carbocation resembles the famous oh my God, benzihydryl cation, that's trityl cation, and the anthracenyl type benzylic cations, where the positive charge is spread over multiple aromatic rings. Hence, huge resonance stabilization. Now, for this question in exam shortcut is whenever loss of halide produces a carbocation that can be delocalized into two or more aromatic rings, think exceptionally stable carbocation, meaning SN1 likely. Even if the structure looks crowded, SN1 can be very fast because of the carbocation, the stability dominating. So the answer is A. Question number 15. Which is the correct reaction coordinate diagram for the following solvolysis diagram? Reaction. Solvolysis again means SN1. So first you have to identify the substrate. The carbon bearing Br is attached to CH3 and the two carbons of the cyclic ring. So it's a tertiary alkyl bromide. SN1 is favored once again. The mechanism, the slow step, also the rate determining step is RBr, the cleavage of RBr bond, formation of the tertiary carbocation. This is the highest energy barrier. So step 1, H2O attacks, meaning R plus gives ROH2 plus, forming a protonated alcohol. This is of course a fast step. Then another fast step, deprotonation, which will be left with ROH. So, how many transition states are there? Each elementary step has one TS. Ionization is TS1, water attack is TS2, deprotonation is TS3. So, the energy diagram must have three peaks and two intermediates. And which has the highest peak? TS1 greater than TS2 greater than TS3. So that means the first peak has to be the highest. Now let's look at your options. A only has two peaks, incorrect. C also has only two peaks, incorrect. D has only two peaks, incorrect. B has three peaks and the first peak is the highest. So B is the answer. And the shortcut for this, for ordinary SN1 solvers, Rx three elementary steps equal to three peaks. So the rate determining carbocation formation is the first peak, which is also the highest. Now for question number 16. The substrate is this. The black carbon is 14C labeled carbon and the oxygen is unlabeled. OTS is equal to tosylate, which is an excellent leaving group. So, and the reagent is OC, RCHCO2H, which is a carboxylic acid. The key concept here is the benzylic. This is a benzylic tosylate. The benzyl system undergoes SN1 very easily because the benzylic carbocation is resonance stabilized. So first pH forms a carbocation. The CO bond breaks, but not a OTS bond. The oxygen leaves with the tosylate, then a nucleophilic attack happens. The carboxylic acid, the carboxylate attacks the benzylic carbocation, so you get P dash. The oxygen, the product comes from the carboxylate, not the original substrate oxygen. So track the labels. Initially, the oxygen over here, after SN1, that oxygen leaves with TSO minus. Then the product is this, where the oxygen is supplied by the carboxylate. The 14C remains attached to the benzylic, and that corresponds with option A. But why not B, you might be asking. B would require the cleavage of the benzylic CO bond followed by an attack on the oxygen, effectively moving the labeled carbon to the other side of the oxygen. That is not what happens in SN1, the substitution of benzylic tosylate. So the answer A. Now for question number 17. Step 1. Start the compound with SN. NBS performs the benzylic bromination, not ring bromination. So oidotoluene with NBS gives oido benzyl bromide intermediate, which is A basically gives IC2DR. Yeah, this is step 1. Step 2 would be reaction with the CH3 SNA. CH3 S minus Na plus is a strong nucleophile. The benzylic carbon undergoes SN2 very easily. So here CH2Br plus CH3 SA minus gives ArCH2 SCH3 plus Br minus. The aryl iodine does not react because the aryl halides do not undergo SN2. So option A. Now question 18. Which one of the graphs represents the chi- which one of the following represents the correct graph for SN2 reaction? This is basically uh, testing us how much we know about steric endurance. So for SN2, rate is basically this rate, and the order of reactivity is CH3X greater than primary, greater than secondary, much greater than tertiary, because the backside attack becomes harder as the crowding increases. The x-axis is obviously is this, that is methyl, primary, secondary, and tertiary. Taking logarithms won't change the trend, so this is obviously discontinuous. So therefore, the graph must show a monotonic decrease from left to right. This is showing a decrease. This is not showing a decrease. Same with C and D. So the answer is option A. Quick memory. CH3X for SN2 is the fastest. Primary is fast. Secondary is slow. Tertiary is almost pink. Sorry, zero. Think more crowding gives harder backside attack, which means slower SN2. Now, question number 19. Same question as the previous one, but SN1. For SN1, the rate determining step is the cleavage of the bond with the haloalkane. So the rate depends on the carbocation stability entirely. So first we have to compare the carbocations formed. CH3 plus methyl carbocation, extremely slow, very slow for SN1 because of their extremely unstableness. Now for this, it will be CH3, CH2 plus, primary, but still very unstable. For this also CH2, CH plus, secondary much more stable. And for this, tertiary, carbocation, most stable and fastest for SN1. So now, which one of these is increasing continuously? A is decreasing, so not A. B is constant, so not B. C is increasing, so it's C. The answer is C. D is irregular, so not D. So pair to memorize SN2 rate order is CH3 primary, secondary, tertiary. SN1 tertiary, secondary, primary, methyl group. Now, which one of the following is most reactive towards SN2 reaction? SN2 occurs at this. The transition state develops some positive character at a benzylic carbocation. Therefore, the electron withdrawing groups minus I group and minus M group stabilizes the transition state, which increases the SN2 rate. The electron donating groups plus I and plus M destabilize it, which decreases the SN2 rate. So, option A, electron donating group. So, not you. Unsubstitute benzyl chloride. So, not you either. Then option C, P-Cl, P-Cl, which is a weakly withdrawing overall, not possible. PNO2, strong minus mesomeric effect and strong inductive effect. So, option D. Now, which one of the following the pairs in which the first compound reacts faster than the second compound in the SN1 reaction? Option A, 1 bromobutane versus 2 bromobutane. This is tertiary greater than primary. So this is slower. D, neopentyl type secondary. First one is tertiary bromide. The second is secondary bromide. So of course this is faster. Now for option C, cyclohexyl bromide versus bromocyclohexene. That means LA carbocation is resonance stabilized. Now for option D, third butyl bromide versus third butyl iodide. Same carbocation, different leaving groups. Second one is faster, so the answer is B. Now 22. Find the major product of the following reaction. There is HBr but no peroxide. So no anti-Markovnikov rule. So first the substrate is allylic alcohol, the reagent is excess HBr. So step 1, the OH is replaced by Br, which will give us an allylic bromide, CH2 double bond CH, CH2 Br. Step 2, HBr adds across the double bond. Step 2, for allylic bromide, CH2 double bond CH, CH2Br plus HBr. Markovnikov rule gives CH3 CHBr CH2Br 1 comma 2 dipropane, which matches with option A. Now for question 23. SN1 and SN2 products are the same with excluding stereoisomerism. So we need to substrate where SN1 and SN2 both substitute the same carbon. Even if SN1 racemizes and SN2 inverts, the constitutional product remains identical. First option A, we have 1 chloro, 2 methyl cyclohexane. SN1 will rearrange to a more stable carbocation. SN2 gives direct substitution. So, not possible. Now, option B, 1 chloro, 1 methyl cyclohexane. This leaves the leaving group is on tertiary carbon. SN1 gives substitution at the same carbon. So, option B. Now, for C, 4 methyl cyclohexide hexyl chloride. SN1 and SN2 both replace the same Cl. However, SN1 gives cis or transmixture due to planar carbocation. Still the same constitutional product possible, but the standard answer is usually B. Now, option D, secondary chloride capable of rearrangement under SN1. Now, 24. Consider the nucleophile attacks given below. Select in each way that shows the greater SN2 reaction rate. A has isobutyl bromide as 1, 2 as a corresponding acetate ester. For SN2, Br is a much better leaving group. Put an acetate, attach it through oxygen. So 1. So this is 1. Yeah. Now B. Okay. Now B. C 3 and 4. CH3SS and CH3SH2 plus. Wait, there is no plus. Sorry. The nucleophile is thiol in both drawings, but 3 corresponds to the less hindered and better nucleophilic situation. So 3. C 5 and 6. Cyclohexyl bromide plus Cl minus with cyclohexyl bromide plus iodide minus and DMSO. I is polar aprotic, which is DMSO, which is a stronger nucleophile. So 4, sorry 6. Now D, the cyclohexyl bromide Cl minus or cyclohexyl bromide I minus in methanol. Methanol is strongly solve as I minus and reduces nucleophilicity. So Cl in the other case wins. So 7. So the answer is D. 1, 3. Wait a minute. Yeah, okay. Question 25. Which one of the two stereoisomerisms of 4-butyl cyclohexyl iodide will undergo SN2 substitution with 128 I minus faster and why? This is a famous axial versus equatorial halide question. For SN2, backside attack is needed. So for structure A, the backside attack is hindered by the ringwork framework. SN2 is slower. Now this is axial. Backside attack can occur along CI. So as CI access much more easily. So SN2 is faster. Therefore, B reacts faster. Why? Because it leads to the more stable equatorial halide after inversion and a transition state lowers the energy. So, option B. Now, question number 26. Z-butene reacts with H2, undergoes anti-addition to form a bromohydrin. Since the alkene is symmetrical, you get racemic bromide. Racemic bromide. So this is racemic bromo bromohydrin. So that means CH3 CH O CH Br CH3 with OH and Br anti. Step 2 is uh, deproteination. Deprotonates the alcohol. So ROH, RO minus. Then the alcohol oxide attacks intermolecularly by SN2. So the carbon bearing Br on the carbon at a bearing Br. So the SN2 causes inversion at the Br bearing carbon. The bromohydrin was anti and the inversion produced an epoxide. For a cis alkene, which is the final epoxy is cis dimethyl lozyrene that corresponds with C and only C. Now for question 26. Rank the following species in order decreasing the nucleophilicity in a polar protic solvent, most to least. So first we have propoxide, propylthiolate, and acetate. The key rules are in polar propertic solvents, sulfur anions are less strongly solvated than oxygen ions. Therefore, my bad. Therefore, Rs minus is greater than Ro minus. Also, acetate is resonance stabilized. So, CH3COO minus. So, It has much less nucleophilicity. Therefore, option D. Question 28. Identify the products of the given reactions. This is a neighboring group participation question, also known as NGP question. The substrate has OTS, an excellent leaving group, and NME2 adjacent. Now what happens? The lone pair on nitrogen attacks immediately, forming an azridinium ion. Then the acetate attacks from backside, opening a ring. Because the mechanism passes through the same symmetric azridinium intermediate, both reaction 1 reaction 2 give the same stereochemical product. The net is double inversion and retention, giving retention. At the carbon where OT was originally attached. Thus, a single product is obtained in both reactions, which is option D. Now, question 29. Which one of the following is true about the given graphs A and B? Yeah, A is supposed to be increasing over, not decreasing. Yeah, the rate increases as substitution increases. The x-axis gives us basically methyl, primary, secondary, and tertiary. So the rate increases as substitution increases. This is a characteristic of SN1, carbocation stability, right? So, and graph D decreasing. As the rate decreases, steric hindrance increases, which also corresponds with CH3 greater than primary, greater than secondary, and greater than tertiary, which is SN2. Right? So the answer is option A. In each of the following groups, which is the strongest or best nucleophile? So first, we have to compare CH3O minus, C2H5O minus, and CH3S minus in MEOH for 1. So in polar prokaryotic solvent, prokaryotic solvent, Rs is greater than Ro because sulfur is strongly solvated. So the strongest in all of these is 3. In 2, we have to compare OH minus, H2 and NH2 in DMF. DMF is polar aprotic, meaning nucleophilicity parallels basicity. So NH2 minus greater than OH minus greater than H2O. The strongest is once again 3. Now for option 3, you have to compare isoperox peroxide, third butoxide, and methoid in DMSO. SN2 nucleophilicity depends strongly on steric endurance. In DMSO, CH3O minus greater than I zero. So the strongest nucleophile is 3 once again. So the answer is, wait, not 3, sorry, 2 in this case. Yeah. So the answer is A. Now the substrate is this with NaNH2. Step 1, NaH2 removes a proton from the chain. The chain undergoes intermolecular SN2. So count carbons SO2PH CH2 5-Cl. Now the cyclization occurs between terminal carbon and carbon bearing Cl. A 5-membered ring forms. So the product needs to have 5 rings. So the product is cyclopentane attached to a sulfone, which matches option B. Now, which one of the following is elimination reaction? Now, cyclohexane. Now, elimination reaction basically gives a double bond in the products. Double bond, double bond. No double bond, not possible. So, option D. So, alcohol gives alkene. This is dehalogenation, which is also elimination. So, cyclohexane, this is not elimination because because it's substituted with OCH3. So, option D. Now, question number 33. We have to substrate 2 chloromethyl furan. Furan. I don't know how to pronounce it. So, furan is CH2Cl with the reagent CH3ONA or CH3OH. And the questions explicitly mentions SN1. So, step 1, formation of perfluoryl carbocation. So, furan CH2Cl gives furan CH2. This is a fluoryl, I don't know, perfluoryl cation, which is highly resonance stabilized. Okay, so the positive charge can delocalize furan CH2 plus ring carbocation forms. Thus, the methanol can attack at CH2 carbon. It gives furan CH2 OCH3. So, option A. At resonance positions on the ring, attack at the ring the carbocation positions gives products B and C. But since the question states SN1, SN1 proceeds to the delocalized carbocation. All 3 reactions are still possible. So, option D is the correct answer. Now, what is the principal product of the following reaction? So the substrate is Fischer reaction once again. NH3 is a strong nucleophile, so of course substitution. Now, which halogen reacts? The top uh, carbon is secondary. Bottom carbon, wait, sorry, yeah, my bad. Yeah, the top carbon here and the bottom carbon here. This is secondary. This is also secondary. So now it depends on the leaving group ability. Br minus is greater than Cl. So the substitution occurs preferentiability at the bromine bearing carbon, right? So Br leaves. Then SN2 gives inversion, right? So at the upper stereo center, before it looks like this, after it looks like this. So the answer is option C. Wait, yeah, option C. Now, what would be effect of increasing solvent polarity on the rate of each of the following reactions? Nu being neutral nucleophile. In a reaction a typical example will be H2O plus RCl. Increasing solvent polarity stabilizes the polarized transition state and helps with ionization. So the rate increases. For B charged nucleophile, Nu plus R dash L, the increasing polarity stabilizes the nucleophile more strongly than the transition state. So nucleophilicity decreases, rate generally also decreases. So B. So now, yeah, for question 36, which one of the following is more reactive towards SN2 reaction? Now the options are A. Allyl chloride, B. Benzyl chloride, C. Chloromethyl methyl ether, D. Phenacetyl chloride. Now the SN2 trend is accelerated when the transition state is stabilized. So allyl chloride resonance stabilized. The more ticks, the more stabilized it is. Yeah, okay. Stronger benzyl chloride has stronger resonance stabilization. Now chloromethyl ether. Oxygen exerts a plus I effect. Wait, no, minus I effect and helping somewhat. Now D. Uh, the carbonyl strongly withdraws electron and stabilizes the transition the most. Okay? So the usual order is D greater than A greater than C. Now, Question 37. The product B. We're looking for the product B. So step 1, formation of alkoxide. So step 1, HO minus, I'll write it somewhere else. Yeah, better. HOCH2 4-Cl plus OH minus gives Cl. Now 2, SN2 intramolecular SN2. The alkoxide attacks carbon bearing Cl. So gives a cyclic ether. So count the atoms in the ring, which are CH2, CH2, CH2. That the chain contains 4 carbons, right? Closing the ring gives 4 carbon atoms and 1 oxygen. So 5-membered ring. This is THF or tetrahydrofuran, which matches option B. Yeah, I can give an answer. Okay. Now question number 38. First component. Okay. Remember that SN2 plus steric hindrance plus resonance plus better leaving group, right? So A, this is secondary, this is primary. In SN2, primary is greater than secondary. This is not faster. Now for B, same substrate, different leaving groups. In this case, I is greater than Br minus. This is faster, obviously. So that's not it. Now for C, benzylic bromide versus N-propyl benzide. Benzyl bromide is exceptionally fast in SN2 due to resonance stabilization. So that means option C. Now for option D, an allylic chloride versus vinyl chloride. Vinyl halides almost never undergo SN2, while allylic chloride undergoes readily. Right, no, sorry. Well, ready. So the first is faster. Even option D. Since the question asks in which way the first is more reactive, both C and D satisfy. So the answer is probably both of them. Anyways, question number 39. Secondary reaction is more reactive than the first toward SN2. Ethyl chloride plus ethanol. ETO minus ETOH. First is faster here as well. No. Ethyl chloride plus diethyl ether versus ethyl chloride versus diethyl sulfate. Sulfur nucleophiles are stronger than oxygen nucleophiles. So, second is faster. B. Now, question number C. Ethyl chloride plus metaoxide versus ethyl chloride plus metaoxide. The rate is right. So, the second is also faster. Now, for our option D, ethyl bromide plus PTH3 versus ethyl bromide plus NTH3. Now, phosphines are much better nucleophiles than amines, but the first one is faster, so not even option D. Now, question number 40. Again, same type of questions. SN1 is faster in polar probiotic, right? So H2O is greater than TBOH. Not the case. Third butyl fluoride in methanol versus third butyl bromide in water. SN1 depends on leaving group and solvent polarity. Br minus is greater than Cl minus and water is more ionizing than methanol. So option B. Now, okay. Third butyl chloride in water versus third butyl chloride in water. 1m, 2m, that's the only difference. SN1 rate is depending on carbocation entirely, independent of nucleophile concentration. So no increase. So not even option C. Option D, no, for obvious reasons. Now, question number 41. Which one of the following is true statement about transition state of SN2 reaction? SN2 looks like NuCl leaving group. A closely resembles a carbocation intermediate. SN2 has no intermediate. D, the electrophile is responsible for the reaction. No electrophile plus nucleophile determine the rate. Now for C, lower is energy than the starting materials. The transition states are always higher than the reactants themselves. Also no. Transition state are always higher energy than reactants. So also false. Involves both nucleophile and electrophile. True. Now, question number 42. Increasing the concentration of a nucleophile in a typical SN2 reaction by a factor of 10 will cause the rate to. In SN2, the rate equal to concentration of carbocation and concentration of nucleophile. Now, if nucleophile is multiplied by 10, then the rate will also be multiplied by 10. So the answer is A. Now, decreasing in the concentration of an electrophile in a typical SN2 reaction by a factor of 3 will cause the reaction ratio to. Again, rate equal to KRX nu if Rx is divided by 3, then rate is also divided by 3. Option C. Last two questions for today. For an SN2 reaction, rate is, let me get some space. Rate equal to electrophile and nucleophile. Electrophile is increased by 3 and this is also increased by 3. So overall 3 times 3 equal to 9. So the rate becomes increased by 9. Now question number 45. The reagent is NaSCH2CH3. This is a strong nucleophile and weak base. So the reaction undergoes SN2. First, we have to identify the stereochemistry. In the substrate, we have Br2 as a solid wedge, which means it's coming out. H is shown as a double less dashed wedge, meaning going back. For SN2, there's of course Walden inversion. Therefore, after substitution, this will occupy the opposite of where Br was, and Hn, the Br will occupy swap their places, front and back. So, which one of these will follow that case? A does not, B does not, D does not, C does. Answer is C. That's about it.